Yeah, so the tutorial is not in computable model theory. It has some computable model theory, mostly in this, the part on Thursday. So today is mostly a higher recursion theory, which Yang asked me, invited me to give, and he's told me that to give a tutorial for the grad students so they can follow the rest. I see like 3 grad students around. So for the other ones, this talk is not for you guys. But Doyan said that it's being filmed, so there are people in the internet that might appreciate if I go slow. So the plan, well, I mean, at least what I had planned, I could speed it up because of the audience, was to go very slow through the beginning of recursion theory, but at levels that are higher than arithmetic. This was the plan. This is the plan. I'm going through those 5 topics. So the first hour is on pi11 sets and ordinals. That's like kind of very basic. And then hyperarithmetic sets. And then topic number 3 and topic number 4 is overspill arguments. So all those 1, 2, and 4 is material from 50s and 60s. And then 3 and 5 are related to work that I've done. So I put it in. So that's a bit more advanced, and I guess I can go a bit faster on those. So I guess for the ones that are already bored, because the other things, that part that's going to have. So the last part has a new proof, like the motivated with conversations with Noam and Dan of this theorem from a few years. And part 3 is also like 2 or 3 years old, or maybe 4 years old. All right, and I'm guessing that today we'll probably go to get to the middle of section 3. We'll see how it goes. For the ones that know everything, one thing you could do is try to find the best proofs for the theorems that I'm going to say. And if you find one that is better than mine, let me know. I don't want, or shorter, or I don't know. Okay, so part 1. pi11 sets and ordinals. So I guess lower recursion, I don't know if that is a recursion theory, but the part that is not higher. Lower recursion theory is usually around like 1 jump, like it's complexity. It's complexity theory, but around computable sets, 1 jump, maybe a few jumps. But within the arithmetic hierarchy, no? And at least when I think of higher recursion theory, I think of what happens when you go beyond the arithmetic sets, the things you can define in first order arithmetic. And then in there you have all the hyperarithmetic sets. That's the second topic. And then the first level after hyperarithmetic sets is the pi11 sets, which are easier to define in the hyperarithmetic sets. So let's go talk about the pi11 sets for a bit. All right, ordinals. I know, I assume everybody knows this slide, but just since part 1, pi11 sets and ordinals are very, very connected. Like when we work on pi11 sets and we work on ordinals, they kind of merge into kind of the same things. So I guess if the whole part is about ordinals, maybe I should say what ordinals are. They start with 0, 1, 2, 3, 4, then you have omega, omega plus 1, omega plus 2. You have that one, goes on, and they go 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 on. And on, and on, and on, and on, and on. They go on. It's a lot of ordinals out there. The formal definition is that you have a linear ordering is well ordered. We'll use this notion a million times, so I guess it's worth saying it. If every subset has the least element, I guess Ted put this definition up today. And an ordinal it's just, it means it's an isomorphism type of well ordering. So you just, isomorphism types means like an equivalence class under the isomorphism relation. And they look like those up there. You can prove that this is probably one of the main properties about ordinals. Whenever you have two well-ordered sets, A and B, one of them has to be isomorphic to an initial segment of the other. So they fit like, either like this or like this. So if you look at all the well-orderings themselves, they are well-ordered under this embeddability relation or being an initial segment relation. So the ordinals themselves are well-ordered. Okay, so this one I assume everybody knew. Okay, so Pi11. So basic definition. So an Pi11 formula is one of the form for every function from the natural numbers to the natural number. Something happens of f, and that something is an arithmetic formula. Arithmetic formula means it only has, it's about a number theory, plus, times, less than or equal on the natural numbers, and it has only quantifiers. Arithmetic formula has only quantifiers over the natural numbers, right? So we're putting the for all quantifiers. So the pi is for the for all. The one on top here is because it's a second order quantifier. Cool. All right. So and the connection with well orders, and I give, let's see a proof in a few slides. The connection is that one. If you have a set of natural numbers, then the set is Pi11. So a set is Pi11 means it's definable by a Pi11 formula. If and only if there is a computable list of linear orderings, L sub E, such that for each natural number E belongs to the set, if and only if L sub E is well ordered. Yeah. And one direction is very easy, right? If I guess I didn't write it down. No. Being well ordered, it's a Pi11 property, right? Because you have to say for every function that is trying to code a descending sequence, the function is not a descending sequence. There is a number such that f of n plus 1 is not smaller than f of n. Yeah. So for every sequence, there is a number such as f of n plus 1 is not smaller than f of n in the linear ordering. So it's a Pi11 property being well ordered. The other direction requires just playing with syntax a little bit. I'll do it a bit later. But then that's that theorem is what makes the connection, and at least the way I feel this theory is I'm constantly going from how you write the Pi11 definition of something, you move to ordinals, you work with ordinals, you move back to Pi11. That's what happens the whole time. And so, well, I guess to prove that direction, and also for like most of the proofs in this area, what connects Pi11 sets and well orders are well-founded trees. So let's talk a little bit about trees, because they are essentially what's in between these two notions. Okay, so a tree, by a tree I just mean a downward closed subset of set of strings of natural numbers. We say it's well-founded if it has no infinite paths. Right? So the tree is a set of sequences of natural numbers closed downwards. It's well-founded if it has no path that is infinite. Like whenever you follow a path, eventually it stops. The main notion, when you have trees, you can define a rank on them. I guess this definition assumes a lot of things, but it works. I mean, to proving that it works assumes transfinite recursion. So the rank of a tree is defined as follows. If the tree has only one element, and just like the root, it has rank 0. If it has one element and all the elements below and only one, like sequence of height 1, that's rank 1. If all the elements below you have rank alpha, you have rank alpha plus 1. So in that one up there, if you have your tree, this is the root, so the tree, you have 0, 1, 2, 3. And then you call this tree T0. I'm going to use this picture again later. T1, T2, so on and so forth. The rank of the whole tree, you calculate the rank of each of these branches, add 1 and take it supreme. Add 1 because you have to add 1, supreme of all of those. Yeah, so essentially it tells you somewhat what's the depth of the tree in some sense, how well ordered it is. If a T is not well founded, we say that it's ill founded, and in that case we're going to say that it has rank infinity. Does it work well? Oh, by the way, the rank of a tree is not necessarily a natural number, right? It can be in any ordinal. Countable ordinal, I guess, in this case. This rank is not a computable function, and that's very important. It takes, if a tree has rank alpha, it's going to take you roughly alpha jumps, alpha iterates of the jumps. We're going to see what that means to compute the rank. And here is a very useful lemma when working with trees. So if you have two trees, S and T, the rank of S is less than or equal to the rank of T, if and only if there is an inclusion, a strict inclusion preserving embedding from S to T. Maybe embedding is not the right word, at least with the notation we used today earlier. So I don't mean here one-to-one. It could be not one-to-one, this one. The property here, the only property I ask for this map is that if you have one string strictly included in another, the image is strictly included in the other corresponding. Should we see why this is true? Or what do you guys say? Maybe it's too easy? Let's see. So, any ideas, Ted? So I tell you the quick ideas. This one, if you have a function from S to T that is preserves strict inclusion, then while the proof goes, you have to show that for every string in the tree S, the rank of S of the extensions of sigma in S, as sigma is a set of tau such that sigma concatenated by tau belongs to S. So if here is sigma, that's this sigma. What's the tree above sigma? You have to show that the rank of this one is less than or equal the rank of T of F of sigma. And this is something you can easily show by induction on the rank of sigma, by transfinite induction on the rank of sigma. Yeah, I don't think I want to do all the details, but essentially that's what's going on, right? So this is, yeah, for every sigma here, you prove that I use recursion, transfinite recursion. To show that. For this one, now you have your tree S and your tree T, and you need to define a map. Well, okay, so you got to map the root to the root. There's only one way of doing that. And then you start defining the map one by one. So first all the things of level 1, then all the things of level 2. And you have to make sure at every step that if this is sigma, you have to make sure that your map satisfies this property along the way. You start satisfying this property because of the assumption that the rank of S is less than or equal to T. And then you know that whenever you have something below here, since the rank of this one is less than the rank of that one, the rank of this one is strictly less than that one, so there has to be something here with the right rank. And you just build it step by step. Yeah, that was a quiz. It's not computable. Which one? It's not computable. No, the embedding is not computable. Okay, so if you want, that's the reason it's not computable. If you want to, if you're gonna be picky, you just gave a reason why it's not computable. If you want to interpret it some other way, well, there is some other way. So, yeah, there is no way to compute it. Let's say there is no way to calculate it. Okay, so that's well-founded trees. And well-founded trees in terms of complexity are essentially the same as ordinals. So we can move from one to the other. And I want to give you like the ways you transform trees into linear ordinals and back, because we'll use that in a few proofs later. So first we look for a way of transforming linear orderings into trees in a way that well-orderedness becomes well-foundedness. And it's very simple. So given a linear ordering, you define the tree of descending sequences of that linear ordering. So the tuples, the elements of the tree are just the tuples from the linear ordering, which are descending. And very easily you get that the linear ordering is well-ordered if and only if the tree is well-founded. Because if you have an infinite descending sequence in L, that will give you an infinite path in T, and vice versa. An infinite path in T will be an infinite descending sequence in L. So that's a way of going from well-orders to trees. This is it's a computable operation. Very computable and simple operation, going from trees. What about the rank? What is the rank of this tree? The rank is exactly the linear order you started with. Yeah, and if you want, the reason is that if you take the rank of this TL extending a string sigma, you have to prove by induction that that's the same thing as the last element of sigma, which belongs to so L up to the last element of sigma. So it's again another transfinite recursion to show that you get the same rank. So this construction is very simple. So you get that deciding if a linear order is well-ordered is as hard as deciding. It can be reduced to deciding if a tree is well-founded. What about going from trees to linear orderings? Well, in that case, the operation is the Kleene-Brouwer ordering is this one has at least some content. This one is not as trivial. So first you define an ordering on all the finite tuples of natural numbers, which we're going to call the Kleene-Brouwer ordering. The Kleene-Brouwer ordering is defined as follows. If you have, maybe before you read that, if you have two strings that are incomparable, you use the lexicographic ordering. But if you have two strings that are comparable, you use the opposite of what you use in the lexicographic ordering, which is the longest string is smaller in the Kleene Brouwer. Okay, so that's what it says over there. So sigma is smaller than tau in the Kleene Brouwer if either sigma is longer or there exists an I such that sigma and tau are equal up to I, but the first time they diverge, sigma is less than tau. So that's the lexicographic ordering for incomparable strings. Okay, so that's an ordering of strings. It's a linear ordering of strings. And if you have a tree, you can look at the restriction of this ordering on the tree. And what you get is that the tree is well founded if and only if this linear ordering is well ordered. I guess it's very easy to see if T is not well founded, has an infinite descending sequence. So they are all an infinite sequence, they are all containing each other. So they will satisfy this, so that you will get a descending sequence in Kleene Brouwer. If you have a descending sequence in this one, they don't necessarily, maybe it's because of the lexicographic part, so it's a bit more complicated to build a descending sequence in the tree. But you can see that it's well ordered, because what does the Kleene Brouwer look like? So this is T up here, so here is T, and this is T0, T1, T2. The Kleene Brouwer is going to look like what? So this one is the first element. This one is, the top element. Right? It's included in all the other ones. So this one, it's top element in the Kleene Brouwer. And then, well, all the ones in this tree are less than or equal, all the ones here are less than or equal, less than all the ones here. So you get, here first you get T0 ordered by Kleene Brouwer, and then you get T1 ordered by Kleene Brouwer, and then you get T2 ordered by Kleene Brouwer. And all the branches, and on top you put this one. So if you know, let's say by transfinite recursion, that all of these have to be well ordered, because T is well ordered, then the whole thing has to be well ordered. So that's what it looks like. It has one element at the end. What is the rank of this Kleene Brouwer ordering? Anybody knows? How to get the rank from the tree? From the rank, no, well, the length, because it's a linear ordering. Anybody? Oh, okay, something new for you. So the rank, so the Kleene Brouwer ordering of T is, well, it's not precise what it is. It depends on the tree. But it is between the rank of the tree and omega to the rank of the tree. I guess with the plus ones. The plus ones because you have this plus one up here. And so that again can be proved by transfinite recursion. And you can see it essentially, with the transfinite recursion essentially from the picture here. So this one, so it's going to be larger than the supreme, than each of these plus one. That's in the case of the rank, you just take the supremum of the ranks of each one of these. And it's less than or equal omega to the rank of 3 because here you have an omega sum. And then you use the recursion. And actually, if you have an ordinal alpha, you can always get a tree whose where you get equality here, and the rank is alpha. And you can also get a tree where you get also rank alpha and the equality here. So for each alpha is a tree of rank alpha where you can either get this equality or this equality. So it depends on the shape of the tree whether you get one or the other. Okay, so the corollary is that deciding if a tree is well-founded can be reduced to deciding if a linear ordering is well-ordered. So the two questions are essentially the same. Okay, so linear orderings and trees are the same in this sense. So now we're going to define this set that was mentioned before in both talks. Clean is O. It's not the standard definition of clean is O. So I'm defining clean is O as a set of indices for computable well orders. And these are well orders of whose domain is a subset of the natural numbers. So let's say the natural numbers. So they are binary relations in the natural numbers, which are computable. They have an index. They have all the indices for computable orders. That's clean ISO. So in this case, I'm only talking about clean ISO up to many 1 degree. If all you care is about clean ISO is up to many 1 equivalence, then this definition is the same as clean ISO original definition, because you get something that is many 1 equivalent. And you could have used well-founded trees there, and you get also the same many 1 degree by what we proved in the previous two slides. You can reduce in a many 1 ways well-orders and well-founded trees. The clean ISO original definition had a bit more structure, but not that much more structure, because here also you have the property that each element of O is assigned an ordinal. That's the same thing in the HDD and his original definition. And the most important property of O is that it's pi-1 complete. So usually clean ISO is just a name for the M pi-1 complete set. The same as zero jump is a name for the M sigma01 complete set. So I have a proof of this. Again, I don't know for the audience. And the proof of this is essentially the same proof as that one for the first theorem that said if a set is pi-1, if and only if there is a sequence of computable linear orderings where B in the set is the same as being well ordered. I can tell you what the steps are. So the first, I guess here I use Sigma11 formulas, but they're just the complements of pi-1 formulas. Sigma11 formulas. Oh, maybe I shouldn't have erased this one. So there are a few steps for this. So Sigma11 formulas, they are of the form that exists a function such that phi of f and maybe has a variable for a natural number where this is arithmetic. That's a Sigma11 formula. The first step, and this is due to Kleene, is to transform this formula into one where this one, instead of being arithmetic, is pi01. So arithmetic, this one might be of the form for every x1 there exists an x2, for every x3 there exists x4, such that something f n x1, x2, x3, x4. So you may have many quantifiers being arithmetic, and I want to transform in one that it has only one for all quantifier. Maybe it has a for all here too. For all x5. And the trick for that is to use this column function. So every time you see two quantifiers like this, if you have a formula that says for every x there exists a y psi xy, that's the same thing as saying there exists a function g such that for every x psi of x g of x, where g gives you the witness y for each g, right? So you can transform this into there exists g1 for every x1, and then you have for every x1 for every x2 that exists x4, so you transform that into exists g2 for every x1 x2. So you go and transform each block of two quantifiers and put these existentials up front. And then you put all these existentials together to get one existential function. And then you're going to end up with a for all at the end. Right? So you absorb every existential into, you flip them by, this one becomes second order, and you end up with a for all there. Yeah, so that's Kleene's normal form. And then you have to use, okay, this is lower recursion theory, so I assume these people know that lower recursion theory. If you have a pi01 formula, you can represent it by a tree. So if you have a pi01 formula, it's a computable tree such that a function is going to satisfy the pi01 formula if and only if it's a path through the tree. And actually, if you have a pi01 formula which has a number a variable, you get a computable sequence of trees with the same properties, such as satisfying this is the same as belonging to being a path through a tree. And then you put this together, and then you get that, well, so if S is defined by a pi1 formula, which is the negation of a formula like this one, then M belongs to S. If there exists an F, if there is no F which satisfies this formula, so there is no F, that is a path through Tn. Yeah, because satisfying this formula theta is the same as being a path through Tn, so this is saying Tn has no paths. So belonging to S that is pi11 is the same as saying that the tree has no path, and then that's the same thing as saying the Kleene-Brouwer is well ordered. And that's the same thing as saying the index of this linear ordering belongs to Kleene-Shaw. So that's how you get from any pi11 set, you reduce it to Kleene-Shaw. And notice that even if n is in the pi11 set or not, we always get a linear ordering here. We get that it's going to be well ordered in the case that it's in O, and it's going to be not well ordered when it's not in O. Any questions so far? Any shorter proofs? No? Cool. Yeah, a minute. You know, I wanted, because I'm writing I'm putting these proofs in the book, so it's a better one. I'm going to use that one. Okay, so I guess. Omega 1? In this one? Ah. Yeah, no? It's hard to search omega 1 CK, no? Omega 1 CK, omega 1 Church-Kleene. Okay, so the definition is here. So an ordinal is computable. I want to say that an ordinal is computable if it has a computable representation. So you can define a computable set of pairs that it behaves like a linear ordering, and such that with domain omega is isomorphic to alpha. I guess that's for infinite, and for the finite case you do something. Finite ordinals are also computable. So the computable ordinals are closed downward, because if you have a computable ordinal, you take any elements, you just truncate the ordinal down, you get a computable ordinal. So omega 1 Church-Kleene, omega 1 CK, which for some reason is read first with the subindex and then the superindex, is the least ordinal that does not have a computable representation. There are only countably many computable ordinals because there are only countably many computable programs, so this is a countable ordinal, which to the world of the computable, in the computable world, or it looks like omega 1. It's the first one that you cannot define a bijection with the natural numbers, a computable bijection with the natural numbers. So that's when it's omega 1 relative for the computable people. I don't know. Okay, so Kleene-Shaw, the one that we mentioned before, is pi1 complete set. It can compute a copy of omega 1 CK. How does it do it? Anybody else want to give you a shorter proof? Okay, here is the construction. So you the sum. So O is a subset of the natural numbers. So this is an omega sum, but only for the elements of O, of the linear ordering with index E. All these linear orderings are computable. So they are all below omega 1, strictly below omega 1 CK. every finite sum of these guys is also computable. So finite sum of computable linear orderings is computable. So every initial segment of this one is a computable linear ordering. And by itself, it's omega 1ck because every ordinal below omega 1ck shows up in the sum at some place. So the sum of all these linear orderings is actually omega 1ck. And this is computable from O because you need it here for the index for the sum. Okay, so O can compute omega 1ck, but omega 1ck is not computable. So O is quite powerful in that sense. All right, so that was kind of like the very basic of pi on one sets. Now we move to basic. This is a super important theorem about pi on one set. It's called Sigma11 bounding, and maybe it should have been called it a lemma because you use it as a lemma for a lot of proofs. So it captures something that is extremely useful. Like you use it in a lot of the proofs that appear in the area. You use Sigma11 bounding. And so I wanted to give you a proof of this one. So it says the following: there are various versions of writing Sigma11 bounding. Here is one. So you have a set A that is a subset of clean O, and it's Sigma11. Remember, clean O is pi 1, 1, and actually pi 1, 1 complete. So clean O is not sigma 1. Then there exists an ordinal below omega 1ck such that for all the E's in A, the linear ordering that corresponds to it, which we know has to be well ordered, is below that alpha. Right? So we know all these LEs are below omega 1ck. Here is telling you they're all below some alpha that is strictly below omega 1ck. Okay? So alpha is a computable ordinal. This means alpha is computable ordinal. Okay, so let's see what are the best proofs for this. This is the proof I like the best. So we need to start by defining an operation on trees. It's a computable operation. It takes two trees and returns T star S. It's like a multiplication of trees. It's a merging of trees, which satisfies this property. The rank of T star S is the minimum of the ranks of T and the rank of S. So what is that operation? The operation consists of just merging the two trees into one. So essentially, so T star S is a set of strings of the form. I would like to write. Let me first write this and then fix it. T plus the merging, the zipping of T and sigma, like putting them together. For tau in T, sigma in S, and of the same length. So we consider one for something from T, something from S, and we put them together. Length of sigma. Thank you. And actually, to make the ranks work exactly, what I want to write here, so if I want to write T0, S0 as a pair, T1, S1 as a pair, TK, SK as a pair, where tau is T1, TK, and sigma is S1, SK. So I want this sum to have the same length as tau and as S. So I just, on each coordinate, I put one from tau and one from sigma, one from tau, one from sigma, and put them together. Okay? So we get this tree that is merging both of them. And the claim is that the rank of this tree is the minimum of the ranks of T and S. Why is that? Okay, so first, why is that the rank of T, which one is star S, is less than or equal the rank of T. This is because we have a map that is strictly order preserving from here to here, namely the projection. So projection pi 1 that maps tau plus sigma into tau. So pi 1 goes from T star S to T is inclusion, strict inclusion preserving. Right? So you get that. Why is that the same proof for S? Why is that? Suppose that the rank of T is less than or equal the rank of S. So the minimum one is this one. Then why is that the rank of T is less than or equal the rank of T plus S, T star S? Anybody? Because from here you get a map G from T to S that is strictly a strict inclusion preserving. And then you can define the map here from that maps T tau to T comma to T plus G and tau. And that one is also inclusion preserving. Yeah, so that means that the rank of T is equal to the rank of T times A. Yes. All right, so you get the operation that gives you essentially calculates the minimum of the ranks of two trees. Okay, what's the next step? So we know that A is sigma 1, 1. So the complement is pi 1, 1. So there exists a computable sequence of trees, S of n, such that n belongs to A if and only if Sn is ill-founded, is not well-founded. That's rank infinity. Yeah? So we have that n belongs to A if and only if the rank of Sn is infinity, and we know that n belongs to O if and only if Ln the nth linear ordering is well ordered. All right. So since so for every n, either n belongs to O or n is not in A. So that means that either Ln is well ordered or Sn is well founded. Yet the fact that A is included in O means that either you're in O or you're not in A. So one of these two has to be well ordered or well founded. So then what? Then we can define this. So for each n, this E should be an n. One of these two is well founded, either because n is in O and this is well founded, or n is not in A and this is well founded. So this tree is well founded. So this linear ordering is well ordered. So the sum over all natural numbers is well ordered. And it's computable because this operation star is computable. These LEs are computable. This N is computable. So you get this computable well order. And this computable well order is larger. The rank of this, the Kleene-Brauer of TL, the rank of this guy is at least, if E belongs to A, then we have that T, what is the rank of TLE star Sn? Well, if SE. If E belongs to A, this one is ill-founded, right? So it has rank infinity. So this one is the same as the rank of TLE, because this one is the minimal one. And this one we saw, what I said, I guess, is at least LE. So the rank of this one is greater than LE for all E's in A. So, and then alpha is the sum of all these guys. So alpha is a computable ordinal that bounds all the L sub E for E in A. Yeah? So that's the bound. Alpha is the bound for all the ordinals that belong to A. Okay, so it's a nice combinatorial proof, but it's extremely useful, as we'll see when I use it a lot in what comes next. What's that? You can probably write that in one in one line. Could you say that again? And right. Okay. This is a shorter proof. More constructive. Eh? Yeah, but I use that too. That's good. Thanks, Liang. And I guess, right, so we already know that Kiniso is pi 1 complete. And using the fact that it's pi 1 complete, you can show that it's not sigma 1. Which then you will get this. Okay, so a version, we're not going to use this one today or tomorrow or Thursday, but maybe somebody will use it in the next 2 weeks. It's a similar version of this one, but instead of looking at sets of natural numbers, you look at sets of reals. So now you have a set A, calligraphic A of reals, which is sigma 1, 1 as a set of reals. And all the members of this set are well-orderings of the natural numbers. So they are coding a well-ordering of the natural numbers. And then what you get is that there is a computable ordinal alpha that is bigger than all those well-orderings in the set A. So even when you get, in here you may have a continuum many well-orderings inside this set, but just because it's sigma 1, 1, is bounded. So just the fact that it's bounded by omega 1 sigma k is not obvious, because here you can have a continuum many, you can have well-orderings that are beyond. But even more than that, it's bounded by something that is computable. And the proof is a corollary of that one, and it's a similar idea to what Yang was saying. Well, once you use the other one, is consider a set of indices for linear orderings L sub E, such that L sub E embeds as a linear ordering. There's an embedding, order preserving embedding into some L that belongs to this A. This set A, right? So all the L's, all the E's, such that L sub E embeds in something that is in A. This set is sigma 1, 1 and is contained in O, because first, well, they're all indices, and since A contains only well-orderings, these LE must be well-orders. So all these LEs, all these E's must be in O, because they are all well-ordered. And it's sigma 1, well, because there exists an L, that's sigma 1. A is sigma 1, such that it satisfies the property of being in A, that's sigma 1. And there exists an embedding is sigma 1, because you have to say there exists an embedding, which satisfies the property of being an embedding. So if sigma 1 is contained in O, so by the previous one, there is an alpha, that is a computable ordinal, that is a bound for A, for all these L sub E's. And then that bound has to be a bound for A too. Because if there was something larger than alpha in A, that's something in the calligraphic L, A, it will also be in the little a. Right? So you get the same bound. Yeah, that makes sense? It's like, because, okay, so if alpha plus 1 was embeddable in something that belongs to here, then there will be something of order type alpha plus 1 here, and alpha wouldn't be the bound. So the same bound that you get for A, well, you get the same ordinals in A and E, in the two L's. All right, so that's sigma 1 bounding. So first application has to do with looking at this delta 1 1 sets. So a set is delta 1 1 if it's both pi 1 1 and sigma 1 1. So it has two definitions, one that is pi 1 1 and one that is sigma 1 1. I'm going to use this notation. So if you have an alpha that is below omega 1 ck, I denote this as O sub less than or equal alpha is a set of indices of computable ordinals that are less than or equal alpha. So as alpha approaches omega 1 ck, this gets closer and closer to O. Right? So these are kind of initial segments of O in indices for things that are below alpha. So these guys are delta 1 1. Why is that they are delta 1? Well, they are sigma 1 1 because E belongs to O less than or equal alpha, less than or equal, right? If and only if there exists an embedding from LE to alpha. And also, if and only if, so this is a sigma 1 1 definition. What is the pi 1 1 definition? Well, you have to say E is LE is a well ordering, so E belongs to O, and LE is not greater than alpha, and there is no embedding from alpha plus 1 into LE. That's pi 1 1. Right? So a different way of stating sigma 1 1 bounding will be to say that if you have an A that is sigma 1 and it's included in O, then A is included in one of these guys for a computable alpha. That's the same statement, that's the new notation. And a corollary that we get from sigma 1 bounding is the following characterization of delta 1 1 sets. So a set is delta 1 1 if and only if it's M reducible to this O less than or equal alpha for some computable alpha. For the right to left directions, well, we know these guys are delta 1 1. That's what we said up there. And both the classes of pi 1 1 sets and sigma 1 sets are closed downward under M reducibility. So if this one is sigma 1, so is this one. If this one is pi 1 1, so is this one. So A has to be delta 1. For this direction, we need to use sigma 1 bounding. So we know that A is M reducible to O because it's pi 1 1. We're assuming delta 1 1. So in particular, it's pi 1 1. So it's many 1 reducible to O. Now, A is also sigma 1 1. And therefore, the image under this reduction from A inside O is also sigma 1. So if you have a set that is sigma 1 and is included in O, it has to be bounded. So there is a computable ordinal that bounds this set. So the image of f of A is all included in O less than or equal alpha. So you get that this same reduction is actually also a reduction from A to O less than or equal alpha. Because all the things in A go to less than or equal alpha. Okay, so being delta on 1 defined over here can be defined in terms of many one reductions and all these spine of sets that are clearly so up to less than or equal alpha. Okay, a couple more things. So O, we said it's powerful. We saw it can compute omega 1 ck. Another thing that it can do is compute a path through computable trees. So if you have a computable trees, you can use O to find a path. How do you do that? Well, from each node in the tree, O knows if there is a path from there or not, because he knows if it will sound there or not. So you just start from the beginning and just go into one of the next successors that has a path. So O knows which one it is, and then go on one that has a path, go the one that has a path, and keep on going up, always knowing that you have a path extending it, and O can tell you where to go. We then get that every non-empty Sigma-1 class of reals has a member that is computable in O. I guess I didn't prove this thing the right way. So if you have a Sigma-1 class of reals, this is a basis theorem, says that one of the members of a Sigma-1 class of reals must be computable in O. And I guess the reason is that if you have this class S is Sigma-1, then there exists a tree such that for every x belongs to S, if and only if there exists a function such that x plus f is a path through T. It's essentially the same thing we did when we proved that cleanly so was pi 1 complete. So being sigma 1 is the same as there exists an f that is a path through tree together with x. So once you have this computable tree T, O can find the path through here. So O can not only find the member of the sigma 1 class, it can also find the witness that is a member of the sigma 1 class. So O can find a pair x comma f that belongs to the tree, and that means that x belongs to the sigma 1 class. And actually, it can do more, and this one I'm not going to show. It can find, so if you have a non-empty sigma 1 class of reals, it has a member that is computable in O, and also is low for omega 1. Low for omega 1 means, so x is low for omega 1 if omega 1 relative to x is omega 1 ck. So the least ordinal that is not x computable is omega 1 ck. So, or omega, which is our same, another way of saying this is that omega 1 ck is not computable in x. This will become handy in the next few lectures. Oh, is it? Okay. I'll. Oh, that's why it's. I don't know where I got this reference from, but maybe that's why. For the equivalence. Okay. All right. So I stop now, and then we have go for a coffee break, half an hour coffee break, and then continue with part 2 and the beginning of part 3.